So where did we end up last time? What was the point of stop? Did we agree to predict future? Right? So we are in this physical chemistry. We did a discussion that we do need to describe wave properties of electrons, because all chemicals are made of nucleus and electrons have some wave properties, right? And we got given our certified experts in wave equation, two derivatives here and there. And then we started to discuss Bohr's model, where something is accumulating along the trajectory. Dimensions of energy times time and position times momentum are the same. And this stuff is getting increased as we go along the trajectory, and phase of wave function is changing as this action is increasing. And based on this idea, we suggest that one can guess a wave function at initial time and then apply so-called evolution operator that has exponential with this imaginary action in the phase accumulation that just changes sign in the complex, not sign, but complex projection of wave function, right? So evolution, that will not change absolute value of wave function, but it will accumulate phase at different points of space with different phase. So it will just oscillate and form some patterns. So by now you are experts in evolution operator. And we do need to get to we need to get to the so-called Schrödinger equation, which will be fundamental equation for everything we do later on. So today we will cover two things. We will make a transition from evolution operator to Schrödinger equation, which is really quick. I do not know how to entertain you for like 50 minutes, because this is one line of taking derivative. And second part is I will be, so to say, introducing the concept of commutation and motivating that the thing called commutation is extremely important. But we will not derive much. I will just show one little example. So basically, we will just take two derivatives for the whole class, and for the rest we will be just mumbling from my side and your practice of democracy for the subjects. So why are we doing these presentations? Well, by the end of semester, I need some evidences to assign you great grades. And presentations is probably the best way to accumulate them on one hand. On another hand, things that I'm trying to deliver by now, they are, I do not want to criticize myself, but they're kind of vague and more philosophical. And those things that you are offered to present, they are very well-determined, strict, and structurized. So there are less ambiguities, and they are available not only in this little note, but in any textbook, very many places online. So any textbook on physical chemistry, on quantum chemistry, anything that has word quantum, you have them. And there is just Wikipedia page, so you can make great slides based on public data. And we will split 50 minutes between 6 presentations, which like 4 or 5 minutes, plus time to walk or something like that. The concept that you're going to present will be backup for this Schrödinger equation. They will summarize our philosophical discussions that we had in more organized way. So if you, right now there is no time to read in detail, but later on when you read, you will see that mostly all things that we discussed are covered or partially covered, and they will not be a big surprise. You will not work on them like for the first time. Schrödinger equation itself is like last thing in the number 6. I don't know if anyone has already signed for it, but this is the differential equation that allows to predict the wave function at any point of time, at any point of space, if there is an initial condition. And these two things, evolution operator and Schrödinger equation, they are serving the same goal. In some sense, they're equivalent. But evolution operator is more related to several hundred years of experience of humankind with classical mechanics. But the problem with evolution operator is that it's very hard to solve either by pen and paper or by computers. So it's not comfortable for solving practical properties. And one of the things that is non-local, the initial and final time can be very far, and just from experience, predicting far future is not easy. If the past and future are in the vicinity, in close vicinity in time, all things are getting so much better. Oh, okay. Thanks so much. Very good. Very good. I'll scan and send to your emails. Yes?
We are presenting on the postulates, correct?
Yes, postulates, yes. The second grayish handout is just for your curiosity.
Gotcha.
Okay, so we are focusing on this stuff. And postulates, as many as we can count, will be presented. So just a little refresher of our minds. So the way from past to the future is can be split on several small intervals, and those intervals can be processed as a product of many exponential or as one big exponential with all action in it as an integral. And it just corresponds to accumulation of the phase in the complex plane. Yeah. I'm expected to write things down because it will encourage you to make notes, and I'll try to as much as I can. But while preparing, I'll try to type in as much equations as possible to please your eyes. But some of the notes from previous years are handwritten. So we are progressing with evolution operator. We are progressing forward from the past to the future. And again, our goal is to get to Schrödinger equation, to the equation that locally predicts future from the past. Here with evolution operator, all stuff with Hamiltonian, time, summation, integration, action can be summarized as something that gets from time 0 to time bigger than 0. So I'm going to practice a little mathematical experiment. What if I apply time derivative to the wave function? Just without any intention, just check what is going on. And a little not background, motivation why I want to explore time derivative, because it will show pace, how quickly wave function is changing. So I'm taking time derivative of wave function that depends on position and time, and derivative over time will apply only to dependence on time. So how do I take derivative of a product of two functions? Huh?
Product rule derivatives.
Yeah, which means,
First time derivative, second for second time derivative, third.
okay, so I'm applying derivative to the u times psi plus u times derivative of over psi. And this psi depends on t naught, which is just initial time, initial position that is a constant, right? So suppose that our past is nailed, we cannot change it. If you cannot change the past, then this derivative will be 0. Can change the past. And in the first term, wave function is not changed. And we apply derivative to the evolution operator. The evolution operator does depend on our time that is going on, running, and initial time. Initial time is not affected. Good. Even if we do not derive anything else, there is already a little observation. So time derivative of wave function in the near future depends on the wave function. So it is the same construction. If we need the wave function in the future, we have initial past times some evolution, and then we have the future. And if we need the rate, it also linearly depends. Some operation applied to wave function. So probably we can try to apply derivative to the explicit form of this evolution operator, right? So this is our evolution operator, and we do want to apply derivative to it. So now you see beauty of our original philosophical discussions, and you see the importance of the complex exponential. The Euler equation combined the sines and cosines into exponential, right? On one hand. On another hand, why humans designed exponential? Again, it's all of these mathematical tools are not targeting to torture young minds. They're designed to make life of humans easier. But we have some intellectual barriers to learn some new things. So probably the stuff that we are learning is easier than what it could be. So what is the main beauty of exponential? Why it does have right to live? What is specific about exponential from the point of view of calculus? So derivative of exponential is exponential itself, and integration of exponential is, so it's one of the few, and maybe the only one function that reproduces itself under calculus operations. It's great, especially in this circumstance. Right? So we know that there, as an answer of this operation, there will be an exponential. But as the price of taking the exponential, we need to take derivative of the power of exponential, dt, and everything in this purple brackets, time exponential itself. H bar integral h. So let's think about what will be in this purple circle and how we take derivative over time out of it. Well, first, the constant will just float to the front, right? And you do not need to listen, you can derive it yourself, it's not very complicated. I'm just mumbling it for reference, but it's rather trivial. So minus I over h bar float to the front. And differentiation is inverse to integration, right? So if here is integral and we apply differentiation, it will just remove integration. And then we have this exponential itself, e to the power minus I h bar integral h dt. So we did everything correct, but by now we do not have sufficient information to celebrate. Correct answer always should be beautiful, and we do not see beauty yet. How can we observe that there is something beautiful in here? Any ideas? Okay, what else?
Putting log.
Huh?
Log.
Log is always good. But here I was processing only the derivative of the evolution operator, right? But we started from writing down the derivative of the wave function. What if we plug this purple stuff back here? How would it look like? Then, if you do so, I promise we can identify something that will look really beautiful. And maybe, if you permit me, I'll flip to the next page and try to rewrite it. So you kind of remember this. So, time derivative of wave function equals minus I h bar operator of energy e to the power minus I h bar integral initial time final time h dt integration variable, then here sine x. Are there any terms that we combine together and recall that they have special names? Like, this is a wave function of the past, right? This one is evolution operator. And if we multiply evolution operator by wave function of past, what do we get? Future, correct. So it will be a wave function of future, which is psi of x and t without no. So we can replace this relatively long construction on psi of x and t rather than t naught. And you do not need to rewrite stuff again and again, but I will do it. So d dt of psi v plus minus I h bar operator of energy psi. And arguments here are the same, xt, xt. So we apply this, both psi here and there are future, or maybe present. So they are at the same time. But we are identifying a very important identity. So time derivative of wave function is equivalent to applying operator of energy to wave function. Make sense?
Yeah.
Time derivative of wave function is equivalent to multiplying wave function by energy operator from left. So if you want to see the pace, the rate, how quick wave function is changing, we do not need to take derivative. We can just multiply it by energy operator. And yeah, I would probably even write it down by text. Derivative equals multiply by energy operator. So if you agree with this concept, you are 50% completed the whole course. The rest will be just applications of this equation. So this is major cornerstone. And feel free to think back, challenge the correctness either of your instructor or the equation itself, and try to just recognize where this equation comes from. So we started from waves on a lake, then accumulation of phase and dimensionalities in Bohr atom. Then we introduced evolution operator that changes complex phase of wave function. And then we just applied derivative. So from original thoughts about wave in nature of electron, we came to deterministic equation that can be solved. And the derivative is nothing, by definition, is nothing by subtraction of near past and near future, right? So by this equation, we can progress forward in the next future by steps. And this equation is much more comfortable for solving rather than evolution operator because it is easy to program and relatively easy to solve by pen and paper. What is missing? Like if you are applying common sense, suppose you have nothing to do with science, you're just a great thinker and philosopher, you are over this equation, someone is trying to sell you a point that this equation is beneficial, can predict something, but you're just logically look at it and tell like, Derivative. Okay, I know how to take derivatives. Greek psi depends on position time. Okay. Constant, yeah, I saw it in Wikipedia. Imaginary unit, yeah, I did. H. What is H? Yes, but who gave us this H? Where can I take it if I need to solve this equation? Is it universal H for any problem? So how do we get H? Where to get it? Can we hire someone to construct H for us? Can we look into Wikipedia to get H? So what are your thoughts?
Use a computer.
Computers are used to solve well-defined problems, right? But here, to set up the H is not to solve. It's a job not of a computer, it's a job of a human. So even powerful computers are stupid robots. They need a director, someone to give them good assignments. So H is total energy, right? And energy is kinetic plus potential. Kinetic energy is always the same. And potential depends on what we consider, where our electrons travels, whether it being kept by an atom, or it is free electron in the ancient TV, or maybe just free electron in universe. So or maybe it's electron in a semiconductor quantum dot that ALICE simulates to maybe migrate to a ligand, right? So depending on circumstances, the potential energy will look different. Right? And from our high school and maybe freshman physics, maybe, we get a general idea how to construct potentials for problems. Like if it is square, it will be quadratic function. If it is harmonic oscillator, if it is Coulomb attraction, it will be 1 over r, right? And for kinetic energy, it's just momentum squared over mass, or velocity squared, right? So we have general ideas, but there is an important feature that H for Schrödinger equation needs a replacement of classical variables like position, momentum, angular momentum into their quantum differential operators. And I will get back to it, but if you are extremely hungry for immediate answers, this table shows the correspondence between classical and quantum operators. So basically you write down operator of energy based on your common sense, and then you use this dictionary to convert each variable into its quantum analog. Okay. You already got good half of our today's meeting, and I think it is redundant repetition of what we did. Right? Applying derivative for evolution operator, and we should be Schrödinger equation. Right? There is a little thing. If we use definition of the derivative from calculus, which is near past and near future, or whatever, two nearby points of a function, subtracted and divided by step, right? So if we apply this definition towards our Schrödinger equation, then it will be wave function of a near future minus wave function in the near past or in the present equals to this total energy operator applied to the present wave functions multiplied by step in time. So you see, we took the time step from denominator in the definition of derivative to the right part. Make sense? Okay. And then I want to migrate the wave function of a present from left part to the right part. Then we see that wave function of the near future is equal to the wave function of the present minus this factors times Hamiltonian operator times wave function times time increment. You see, right? So it's nothing but Schrödinger equation in finite differences. And do you see anything that we can simplify on the right part? Anything we can put out of outside of brackets? Yes, yes. We can put it to the far right, and here instead of wave function will be 1. Right? 1 minus this quantum operator times time increment multiplied by past, we'll get the near future. By the way, if we are not aware of Schrödinger equation, but we know only evolution operator, how to get from past to the future. If you expand exponential into Taylor series, does this word clicks any memories? E to the x approximately equals 1 plus x squared over 2 plus 30 over 6, right? So if our, instead of x we have imaginary unit, minus h bar, then this can look as a zero-sum first term in the expansion for the evolution operator. So we are not designing anything new. So those are still same aspects of the different aspects of the same feature. So either from evolution operator or from Schrödinger equation, we have the same way to go forward from past to the future. Okay. 40 minutes. And in the remaining 10 minutes, I want to introduce concept of commutation. Commutation. So you either know what it is, or if you do not know, which do you have any associations or expectations from this word? Like, were you reading Mark Twain, Yankee by the King's Arthur's Court, or maybe movie?
Is it like distribution of things over spots?
In the first lecture in the math department, they do like properties like commutation, distribution, and association, things like that. Linear operators. I see where your thoughts are. So in the relatively, well, maybe not narrow, but in the slice of the community that we will be covering, the word commutation will mean that something is being swapped. And swapping things, well, it is not real world observables. We are now at the math side of physical chemistry and quantum theory. And these objects, like quantum operators, derivatives, wave functions, they are offered in the certain order. And the question is, do we have freedom to swap their order? Like, there are products of things. If you have, let's say, 1 and 2 integer numbers, 1 times 2 or 2 times 1, it is the same, right? So you can swap their order without any penalty. And if we are doing regular algebra, like a square and b cubed, we can swap them and the answer will not change. And now there is a question, do we have this freedom in quantum theory, or it is dangerous and we need to avoid it or do some special tricks? Huh? Tricks, it's dangerous, right? So, if you have a wave function, you multiply it by constant, it doesn't matter. We can multiply it from left or right. If our constant is 1, we can just skip it. But here is an example. If we use the symbol of differential operator, of the derivative, this symbol assumes that it acts from left to the right. So if you consider differential operator as a standalone object, and you want to put it after the function, it will have different meaning. Before it was acting on the function, and now it acts on nothing. Right? So you see this logic. So the order of the objects matters, and we need to be careful. And the simplest possible example is multiplication of 3 objects: derivative of a space, position operator, and function or wave function that depends on x. So derivative over x of x times psi of x. By the rule of product, I can apply it as dx of x times psi plus x times dx over psi, right? No surprise. Now, what is the derivative of x over x? Right. So, derivative ddx of a product, x times psi, equals 1 times psi plus x dx of psi. So I want to rewrite it once again by transferring this last term from right to the left. dx of x times psi minus x dx of psi equals psi. It will be very frequent in what follows if in equations like that we symbolically remove psi or like cancel psi, putting 1 instead of it. But it will not mean that that we completely remove it. It means that instead of function psi, there is something unknown. So we just put a little empty spot here, there, once times here. And in this, no, a little too early. So we will write x dx minus x dx equals 1. So if I wouldn't give it a little introduction, it would look crazy. But it means that something is assumed at this place, here, there, and there. And both derivative and x are now considered as operators. So we are making first step into algebra of operators. And they still obey algebraic logics. There are some rules that we can write down and follow, and little exercises like this will come here and there frequently. So commutation does exist. There is a penalty for swapping order of operators. If you swap the order, there is a penalty. Make sense? You don't need to memorize or do any exercise right now, but you need to get the concept. Okay, you got this little slip. I've got your, let me double check that it is here. I've got your, yes. So, meeting is done. Thank you for your intellectual energy invested in this course. Not yet homeworks, but please start preparing PowerPoints. And you didn't tell me what is your, who votes for Friday? 1, 2, 3, 4.
I don't care. I'm glad.
So Friday is better?
Sure. Let's get it over with.
Yeah, I'm not
We all
applying
present
for
the same day.
all presented the same day. Yes.
Okay.
No splitting, because you will those who are not presenting certain subject will learn. It's a little early for me, but you guys teach each other the subject, right? So Friday accepted. No.
Do you want to vote?
Anyone is
I thought we were.
no. Anyone is strict is a very strong objection against Friday.
I would rather.
Strong objection
Monday,
or
I don't care. So I'm okay about Fridays.
Monday.
so Friday is accepted.
Wait,
No,
I think
Monday.
we wanna do
I think
Monday.
it's
Huh?
opposition to Friday.
We want to do Monday since.
So Monday is better.
With
Yeah.
Monday, yeah.
Okay, but start thinking, collecting information. 4 or 5 minutes is not long, but if you create slides before, it will be easier for them. By now, it is the one assignment.
So is anybody unhappy with the subject that they have? I'm not super set on anything. I'm just like,
I don't love mine, but I will learn.
what one are you?
2.
You two? Okay.
But I'll figure it out.
I feel like 4 is no better than 2, so
Yeah.
they're basically the same.
Yes.
Oh, your feet are getting so wet. Yeah, I know. It doesn't go over.